In 2.6, we're going to talk about what it means for a function to be continuous. Now, when we talk about continuous, we just mean that the function does not have holes or breaks in it. In order to define continuity, we need to use limits. Okay? And then eventually, we're going to put the idea of limits and continuity together to define the main topic in calculus, which would be our derivative. But first, let's look at this graph. Notice that it's a continuous graph that has no breaks or holes in it, meaning if I were to sketch this graph, I wouldn't have to lift up my pen. I can do it in one piece. So if we can do that, we say the function is continuous. The second graph is not continuous. I can sketch the graph, but then I have to stop here. And I have to make a big jump before I can sketch the rest of this graph. And because I made that big jump, we call this a jump discontinuity. Okay, so this particular graph is not continuous at x is equal to 0. So let's look at another graph. Now I could sketch this graph. The problem is, once I get to the point x sub 0, there's this hole that I have to skip over and lift my pen up before I can sketch the rest of this graph. So if there's a hole, we call that a removable discontinuity, because all we really have to do is just plug up the hole. So this is a removable discontinuity. Sometimes we call it a point discontinuity, because it's just a single point that we need to fill in. So the next graph we're going to look at has a vertical asymptote at x is equal to 0. So when I sketch the graph, I'm going to be sketching it in two pieces. Okay? So notice that this is going down to negative infinity, and then when I jump to the other side, the graph is going up to positive infinity. So it makes sense to call that break at x is equal to 0 an infinite discontinuity. So now here's our definition of continuous. A function is continuous at a point if, and it's real simple, the limit is equal to the value of the function. And that's it. As long as the limit is equal to the value of the function, then it's continuous at that point. What we're really going to use when we check for continuity is we're going to use this continuity checklist. Okay? So when we do check to see if a function is continuous, we have to first make sure it's defined, right? There's no hole there. And then we have to check to see if the limit exists. The last thing we check for continuity is that the limit is equal to the value of the function. So condition 3 is just saying that 1 is equal to 2. Now, if all 3 conditions hold, then the function is continuous. So to show that a function is not continuous, all you have to do is show that one of those conditions does not hold. So let's look at example 1. We're going to use this graph to identify the values where the function is not continuous. And then we're going to identify each point of discontinuity as removable, jump, or infinite discontinuity. So I can see when x is equal to -2 that there's a hole there. So this is going to be discontinuous at x is equal to -2. And that would be a removable. So I'm looking at this right here. That would be removable. The next discontinuity would be when x is equal to -1. And you see that there's this big jump in the graph. So that would be a jump discontinuity. However, there is something that we should also note. We should also note that we have 2 open circles here. So even if I were to bring these 2 circles together, these 2 pieces of the graph together, it still would be an open circle. So technically this is also removable, but it's mainly jump, so I'll leave jump discontinuity there. When x is equal to 1, there's another discontinuity. There's a vertical asymptote here. So at that vertical asymptote, that would be an infinite discontinuity. So the next example, we want to determine whether the functions are continuous at the given point. So if you're supposed to show whether or not a function is continuous at a point, you're going to use the checklist. Now we also need to justify our answer, and the justification will just be the checklist. So in example 2a, we're supposed to determine if this function is continuous when x is equal to -3. So the first thing I want to do is look at the first thing on the checklist. Is the function defined? Does f of -3 exist? Well, that would be equal to 10 over 0. So it's undefined. So since it's undefined or not defined, then I can stop. This function is not continuous at -3. So thus, f is not continuous. And instead of writing continuous over and over again, I'm going to just put continuous with a dot. It's not continuous at x equal to -3. Why? The justification is by the continuity checklist. Okay, so one condition is not met, I can stop, it's no longer continuous. Well, let's look at the next example, B. So we're supposed to see if this function is continuous when x is equal to -1. So notice it, x is equal to 1. So notice it when the function breaks up. This is a piecewise function. So let's go ahead and look at the conditions. So the first condition is g defined at 1? So So I have to be careful about which piece of this function I'm using. So at 1, I'm using the upper, which would be the square root function. So this would just be the square root of 0, which is 0. And it's defined. So it meets condition 1. It's defined at 1. So let's look at condition 2. Let's see if the limit exists. Well, the problem is that this is two different functions. So I'm going to have to check the limit coming from the left and coming from the right. So if we look at the limit, as x approaches 1, I'll come in from the left. I have to be really careful. If x is approaching 1 from the left, then I'm going to be using the upper piece. So I need to write that in. It's the square root of 1 minus x, which would be equal to the square root of 0, which is equal to 0. So the limit exists when I'm coming from the left, but I also have to come in from the right as well. Again, the reason why I'm doing this is because at 1, the function breaks up into two pieces. Coming in from the right, I'm actually using the lower piece, because coming in from the right, I'm looking at x values that are larger than 1. So I need to write that in here. X squared minus 2x plus 1. Okay, so that's going to be 1 minus 2 plus 1, which is 0. So notice that coming in from the left and coming in from the right, I have the same limit. So I can conclude that the limit as x approaches 1 of, now I can just put in the generic g of x, is equal to 0. So the limit exists. So conditions 1 and 2 have been met. Let's check condition 3. So condition 3 is easy to check if you've already done 1 and 2. We're just saying, is the limit equal to the value of the function? Is condition 1 equal to condition 2? And yes, it is, because g of 1 is equal to 0, which is equal to the limit as x approaches 1 of g of x. So since all three conditions have been met, we can conclude that g is continuous at x is equal to 1. And the justification is by the continuity checklist. Okay. So that's how we show if a function is continuous or not continuous at a particular point. Now we're going to discuss a bunch of different theorems involving continuity. Okay, so theorem 2.8. All theorem 2.8 is saying is that if you add continuous functions or subtract continuous functions or multiply continuous functions, it's going to be continuous. If you divide continuous functions, it's going to be continuous, provided that you don't create 0 in the denominator. If you multiply a function by some number, still going to be continuous. If you take a continuous function and you raise it to some power, it's still going to be continuous. And the next theorem just talks about polynomial and rational functions, which just says in part A that polynomial functions are continuous for all x. So that just means from negative infinity to positive infinity. And rational functions are going to be continuous for all values except for where the denominator is 0. So we also have a theorem about continuity of composite functions. So composite functions would be putting one function inside another. So let's say that f and g are continuous, and we're putting some a value into g. We're going to get some value, and then we're going to plug that into f. So if f and g are continuous, then the composition f of g is also continuous. And what's nice about it is instead of having the limit on the outside, you can bring the limit to the inside when you evaluate. So you would take the limit of the inside piece, you would get some number, and then you would just plug that into the outside function. In example 3, we're going to kind of put all this stuff together to figure out what f of 3 is. So f and g are continuous, and we know what the limit is. As x goes to 3, the limit of f plus g is going to be 10. And I also know that g of 3 is negative 2. So I'm supposed to find f of 3. Okay. Well, what I know is that the limit as x goes to 3 of f of x plus g of x, I know that that's just going to be equal to f of 3 plus g of 3. Why do I know that? That's the definition of continuous, that the limit is equal to the value of the function. Okay. Well, I also know that g of 3 is equal to negative 2. And this limit has to be equal to 10. So if we put these last two pieces together, that says f of 3 minus 2 is equal to 10. Or in other words, f of 3 is equal to 12. And I'm done. So something that does come up is not just continuous at a point, but what about being continuous on an interval? So when we talk about continuous on intervals, the first thing we want to look at is we want to look at endpoints. It's easy for us to determine whether a function is continuous inside an interval, but the endpoints can give us some problems. So a function is continuous from the left, okay, so coming in from the left, or left continuous, if when you take the limit from the left, it's going to be equal to the value of the function. So again, the limit is equal to the value of the function. It's continuous from the right, or coming in from the right, if when you take the limit coming in from the right, it's going to be equal to the value of the function. So it's the same definition as continuous at a point, except for you're just coming in from one side because it's an endpoint. So we have to talk about continuous and continuous at endpoints so that we can talk about continuity on an interval. So a function is continuous on an interval if it's continuous at all points of the interval. If the interval contains its endpoints, then that means that you have to check to make sure that it's continuous at those endpoints. So that's kind of a lot of words, blah, blah, blah. What does it mean? So let's just go ahead and look at this example here. I'll call this function f. Maybe this would be 1/3. Kind of looks like it. Maybe this y value here will be -1 1/3. Just making it up. So we want to determine the intervals in which the function is continuous. Okay, and we can assume here at the end that they're arrows and they're going on forever and ever. So I can clearly see when I look at this that I have a continuous function because there's no breaks, no holes in that one piece of the graph. The only problem I'm going to have is right at the end here, right? So I could see that it's not continuous when x is equal to positive 1/3. And I could see by looking at the graph that it's going to be continuous on these intervals from negative infinity to 1/3 with a parenthesis because there was this open circle here. And then when I look at the next piece, this is solid and then clearly continuous. So we don't use that union symbol, we use a comma when we're listing intervals of continuity. It's going to be this bracket, and I'm going to include the 1/3, and then we're going to go to positive infinity. So those are the intervals where my graph is continuous. So I'm going to verify this by using limits. Well, this first interval does not contain its endpoints. So when you look at the definition of continuity on an interval, it doesn't say anything about what will happen if it does not contain endpoints. So I don't have to check that first interval. I have to check the second one because it says if the interval contains its endpoints, then continuity means that you have to have continuity from the right or left. So I do have to verify in this interval here, this second interval, I have to verify that it's continuous at 1/3. Okay, so I need to take the limit as x approaches 1/3. The problem is, am I approaching from the left or am I approaching from the right? Well, you can't approach 1/3 from the left because there's nothing there. The only way I can approach 1/3 is from the right. Okay? From the right. So it's a plus. So as x approaches 1/3 from the right, the limit looks like it's going to be -1 and 1/3. Okay, so look at what I just said. I said the limit is -1 and 1/3, but that's also the value of the function at 1/3. So since the limit is equal to the value of the function, then I know that I can include the endpoints when I list my intervals of continuity. So let's add in some more theorems. We're going to look at functions that have roots, like a square root or a cube root. So if you have a function that's raised to an exponent that's rational or a fraction, you have to be careful about what the denominator is. If the denominator is odd, then there's no problem. Wherever f is continuous, f to the nm is also going to be continuous. However, if m is even, we might have an issue. Because even, remember that denominator represents a root, like a square root or a fourth root. So even says that it's going to be continuous where f is continuous. And we also have to make sure that the function is greater than 0. And then we have another theorem about trig functions. And you can use all these theorems when you're trying to show continuity. So it just tells us the trig function sine, cosine, tangent, cotangent, secant, and cosecant are going to be continuous on their domains. So for sine and cosine, that would be negative infinity to positive infinity. But not for tangent, cotangent, secant, and cosecant, because remember, they have asymptotes. Okay, so we're just building up all these theorems on continuity that you may use. So let's go ahead and determine the intervals in which this function is continuous. Well, this is a square root function. So remember, that's the same as x squared minus 4 to the 1/2 power. So notice that we have an issue because 2 is even. Okay. So let's just look at, by the theorem, look at where the function is positive. Okay. So this is going to be positive when x squared minus 4 is positive. So try to figure out all the x values and make this inequality true. But it's a nonlinear inequality. So going back to algebra, the way we solve these is by factoring and finding critical values or critical points. So if I factor x squared minus 4 and then set each of these factors equal to 0, my critical values or points would be x equal to negative 2 and x equal to positive 2. So oftentimes what we do with those critical values is we'll put them on the number line from small to large. And look at this. Remember, we're trying to figure out all the solutions to the inequality x squared minus 4. So if I pick any x value from negative infinity to negative 2 and put that x value into my inequality, it's going to make it true. But I can't use negative 2. So typically we would do an open circle because negative 2 makes it equal to 0, not greater than 0. And then I can use any number greater than 2. It'll make the inequality x squared minus 4 greater than 0 true. But I can't use 2. Alright, so what that means is this function is continuous on the following intervals. Negative infinity to negative 2, comma, not union, 2 to positive infinity. So now all we have to do is check the endpoints to see if we can include them. And that means we want to take the limit and see if the limit is equal to the value of the function. Well, first of all, f of negative 2 is equal to 0, and f of 2 is equal to 0. So when we check the limit as x goes to negative 2, and here notice that we have to approach negative 2 coming in from the left. And this would be the square root of x squared minus 4. This limit is equal to the square root of 4 minus 4, which is equal to 0. Okay, so the value of the function and the limit are the same. That means we can include negative 2. Now let's look at 2. When we take the limit as x approaches 2, it's going to be coming in from the right. And it's x squared minus 4. It's going to be equal to the square root of 4 minus 4, which is equal to 0. So the value of the function and the limit are the same. That means we can include 2. So these are the two intervals of continuity. And moving on to our last example, we're going to be using this idea of continuity to talk about the intermediate value theorem. Okay, so this intermediate value theorem depends on our function being continuous on some closed interval AB. And let's say that we have this number L, and it happens to be between f of A and f of B. So these are y values. L is also a y value. So if the function is continuous and you have some number between f of A and f of B, then this is what we get. We get at least one number, C, in the open interval AB, so that f of C is equal to our number L. So we're going to use this intermediate value theorem to show that this equation, cosine of x equal to x squared minus 3, has a solution in the interval 0 to 2. Now this theorem doesn't tell us what the solution is. What it does is it gives us an existence of a solution. Well, first of all, to use this theorem, I need a function. This is not a function, cosine of x equal to x squared minus 3, but I can create a function by minusing cosine from both sides. So I have something like x squared minus 3 minus cosine of x equal to 0. So I'm going to let f of x equal x squared minus 3 minus cosine of x. Here's my function. So really what this is saying is f of x is equal to 0. So first of all, is this function continuous? To be able to use this theorem, it has to be continuous on AB. In our particular case, AB is 0, 2. And it is, but I have to make some sort of comment about that. First of all, notice that x squared minus 3, this is a polynomial. And cosine of x, that's a trig function. Polynomial is continuous from negative to positive infinity, so all real numbers. And so is cosine. It's continuous from negative infinity to positive infinity. It's got no breaks, no asymptotes. So what we're doing is we're subtracting two continuous functions. And by a previous theorem, f is also going to be continuous. So f is going to be continuous from negative infinity to positive infinity. So since our function f is continuous from negative to positive infinity, clearly f is continuous on the interval from 0 to 2. Okay, so we defined our function. We showed that it was continuous. Now we have to look at f of A, f of B. So this would be my A, and this would be my B. So f of A is f of 0, and f of 0 is going to be equal to -3 minus 1. So that's going to be -4. And f of 2 is going to be equal to 4 minus 3, so 1 minus cosine of 2. So when you put that in a calculator, that's approximately 1.42. So we have to show that our L is between -4 and positive 1.42. But what is L? This is where you find your L. Our function is equal to 0, so L is equal to 0. So notice here, with these two conditions, f of 0 and f of 2, I have that L, which is 0, is between these two values. All right, so we showed f is continuous. We showed L is between f of A and f of B. So because of that, we can conclude that there exists some number C in the interval 0, 2 such that f of C is equal to L, and in our case our L value is 0. Okay. So unfortunately I don't know what that x value is. All I know is that from the intermediate value theorem there is a solution. Okay, so that's it for section 2.6.